Hello everyone. So we are going to start the part 3 from the topic deformation of solids. So in this topic we are going to cover the concept of Young's modulus, strain energy and some other associated concepts which are generally used in the physical pharmaceutics. So without wasting any time, let's start our presentation. The first thing, it is the Young's modulus. So what is Young's modulus? See, by definition, by virtue of definition, Young's modulus, it is defined as the ratio. Young's modulus, it is always defined as a ratio between the tensile strength to that of the tensile strain. Means if we signify Y as a Young's modulus, then Y is equal to tensile stress divided by tensile strain. But the thing is that whenever we are going to put the tensile or give the tensile stress to the object should not cross the proportional limit. This proportional limit we have already discussed in our previous class. The proportional unit is the limit unit till which the Hooke's law or the material it follows the Hooke's law. Now it can be also represented as, you see, Y, that is your Young's modulus. It is equal to tensile stress divided by tensile strain. So tensile stress, what it can be represented with, it can be represented as a F by A. This is actually the sign of perpendicular, right? This is a perpendicular force applied. So F by A, and tensile strain, it is represented by E. It is the extension, right, by the original length. So Y is can be also written as F L naught divided by AE, and its dimension is kg per meter per second square. This is the Young's modulus. Now let's have some basic concept of the Young's modulus. You see, Young's modulus, it never depends upon the length of the wire. I repeat, the Young's modulus, it does not depend upon the length of the wire, but it depends upon the material of the wire, or you can say nature of the wire, of which the material means the Young's modulus, it is independent of the nature, it is independent of the length of extension of a wire, but it depends upon the nature of the material of which the wire it is made. Next thing is that the Young's modulus, it never changes if the length of the wire increases or decreases. Is it clear? The Young's modulus, it never changes if the length of the wire it is increased or decreased. So here I am going to give you the value of Young's modulus of various material. So this is a table. Aluminum, it has a Young's modulus value of 69, copper have 110, steel have 200, nylon it have only 3.7, and glass have 70. Now you are telling the term, or you are using the term Young's modulus. So how you are going to determine the Young's modulus? So the Young's modulus can be determined by using an apparatus. It is known as the Searles apparatus. Searles apparatus. So how it looks like? So this is the Searles apparatus. So in this apparatus there will be two hook. There will have two hook. In one of the hook, the reference wire will be kept. In another hook, the test wire will be kept, right? In the test wire we are going to use one vernier scale. We are going to use one vernier scale which is denoted with V, and in the reference wire we are going to use the principal scale. The principal scale, it is also known as the main scale. This reference wire, it will be tied with a fixed load W. It will be tied with a fixed load W, whereas the test wire, it will be tied with a mass M, which can be increased or decreased every time. Clear? So let's discuss the experiment. You see, the original length, that is the L naught, and the diameter D of the test wire. Original length L naught and the diameter D of the test wire is measured several times. It is measured several times by using the meter rule and a micrometer screw gauge respectively. The length, the original length and diameter of the test wire, it is measured several times. I repeat, the length and diameter of this wire, it is measured several times, many a time, by using a meter rule and a micrometer screw gauge respectively, right? So now using this shearless apparatus as shown in this figure, right, it determines several values of extension E. It will determine several value of extension by adding more amount of the mass. Every time you are going to increase the mass, you can see these are the small disc, right? Every time you can use one disc, you can load one disc to see the extension, small e by adding the mass m gradually. This reading, the mass you can enter here, then the reading of the main scale. The reading of the main scale can be entered here, the vernier caliper will be entered here, and the extension will be entered here, right? Now all the readings obtained in the experiments are recorded in the table as below here. All the reading will be recorded here, and then what will happen? A graph of mass m, a graph of mass and extension will be plotted. So this will give you the value of Young's modulus. So you see how you are going to get it? It's very simple. So from the definition of the tensile stress and tensile strain and Young's modulus, what we have? Y, that is the Young's modulus, it is equal to tensile stress divided by tensile strain. So tensile stress can be defined as F by A, whereas tensile strain it is defined as E by L naught. We also know that this F is equal to what? MA, right? F is equal to MA. That is a Newton first law, right? So in case of A, we can write the G, acceleration due to gravity. F is equal to mg, right? Now just put the value of mg here in this equation. So here we are going to put the value and arranging mg L naught divided by AE. Here in case of F, we are going to put the mg, right? So mg, and it will come in the numerator, this L naught will come in the numerator, so mg L naught by AE. So it can, and this A, it is what? It is the area, right? Area of the cylindrical wire, it is denoted with pi d square divided by 4, right? So this equation, now put the value of A here, what you will get? M, after putting the value of A here, you are going to get M is equal to Y, Young's modulus, pi d square divided by 4g L naught. This E into E, so it's all come into E. Again I repeat, put the value of A here in this equation and then rearrange this value. Then M is equal to what we are going to get? M is equal to Y, right? Pi d square divided by 4g L naught whole into E, and comparing with the Y. So that is the gradient x. So hence the M against E is a straight line through the origin. So this is the straight line and this is the slope. The slope, it is the gradient. The gradient, it is nothing but Y pi d square divided by 4g L naught. Clear? Now you see what is the relationship which exists between the force constant K and the Young's modulus Y for a wire. We know that, see, from the Hooke's law, the force constant is equal to F is equal to KE. It has come from the Hooke's law, right? K, it is the force constant. F is equal to KE. E is the extension. And from Young's modulus, Y is equal to, where Y is equal to, from actually this F, it is here only. So F is equal to Y AE divided by L naught. This is the equation we get from the Young's modulus, right? Now you see here, just equalize this equation. So KE is equal to YAE divided by L naught, where K is equal to YA divided by L naught. So this is the equation, and this is the rearrangement, and this is the relationship between the K, that is the force constant, and the Young's modulus Y. So K is equal to YA divided by L naught. Clear? The next concept, it is the strain energy. So what is the strain energy? You see, the strain energy, very simple. Just remember that whenever a wire is stretched by a load or a force, if we have a wire, if we try to stretch the wire, work is done on the wire, right? And strain, it is also known as the elastic potential, is stored within. Whenever we stretch a wire, the energy we have put in stretching the wire, it is stored in the wire as a elastic potential energy, right? Now let us consider the force extension graph here of this wire until it reaches the proportional limit, means until it reaches the Hooke's law. So this is the force, this is the extension. Till the proportional limit, we can, if we stretch a wire till the proportional limit, now the energy that we have applied on the wire for stretching, this is also denoted as a work done, right? So total amount of the work done in stretching the wire from O to E, from here, suppose from here the wire has been extended to E, so from O to E, the amount of the energy that is wasted or it is used is equal to W, that is the total work done. W is equal to integration 0 to E F dE. dE, it is the small change in the extension, right? That is equal to the shaded area. This is the work done, this is the work done, this is the work done, this shaded area is the work done. So the work done is equal to strain energy, right? Integrating this term, what we are going to get, half Fe, right? Now you see, from the definition of tensile stress and tensile strain, what we got, stress is equal to F by A, that is F is equal to stress into A. Simple. Stress is equal to F by A, so F is equal to, just take this denominator to this left hand side, so F is equal to stress into A. Similarly, strain is equal to E by L naught, thus E is equal to strain into L naught. So strain energy, the strain energy is nothing but half Fe. So half F is equal to F into E, this F and E. So stress into strain, AL naught, that this AL naught, area and length, it is nothing but it is the volume. So here just put the value, strain energy is equal to half, this equation has come from DC only, half Fe. So F is actually stress into area, and E is strain into L naught, so half stress into strain into AL naught. AL naught is nothing but it is the volume, thus you see, strain energy divided by volume, this is the volume, strain energy divided by volume is equal to half stress into strain. Thus this strain energy per unit volume, is the area under the stress strain graph. The strain energy per unit volume is the area under the stress strain graph until it has reached the proportional limit, that is a straight line graph. So I repeat, the strain energy is the area under the stress strain graph. So thank you everyone, hope you have liked the class. If you like the video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.